image segmentation, and this is a more advanced topic. And so far we have studied like basic operations on pixels. So we started from filtering, very basic operation. Then we moved on to edge detection, again, which was used, which was based on the filtering process. Then from edge detection, we moved on to extracting features. And then from extracting features, we move on to how we can utilize those features for, let's say, classification. And then we have seen object detection, where we not only like classify which object is present, we also localize where the object is present. So that's like a bottom-up hierarchy. So we are moving up the hierarchy. So this topic is image segmentation, where the idea is we not only, I think this, someone's mic is on. Are you asking any question? Okay, so yeah, if you are not saying anything, please mute your mic. There is a question from Grace. So that all encompasses image processing. Yes, you can say that, but image processing is like a specific term which covers all this, but that's different from computer vision, because computer vision is more about like understanding what's happening. Image processing is something you perform different kind of operations on the image. So, and there you don't care about like the visual perception. So there's slight difference between these two topics. Okay. And of course there's a lot of overlap. So segmentation is like the next level of image object detection, where you not only localize the object, like you draw the bounding box, but what you do is you also draw a nice boundary around that object. All right, so it's more challenging than object detection. In this lecture, I think this will be the agenda. First, we will try to understand the basics of image segmentation, and we will start with like very basic operation, which is called image binarization. And then we will also talk about also algorithm, which I think you will have to do for your programming assignment 3. So I think we will try to cover this topic today, so that you have enough time to implement this. Then we will move on to like more advanced topics, where we do region-based segmentation. Again, we will talk about 2 different strategies there, merging and splitting. And finally, like to clustering-based approaches, which is like k-means and mean shift algorithm. So these clustering-based algorithms, if you have taken any machine learning course, you should already know what these algorithms are. And then we will see that like how we can use these clustering algorithms for image segmentation. Okay, so this will be like a I think it will take roughly 2 lectures. We will be until here, I think, region-based somewhere, and then the rest we will cover in the next lecture. So let's start with the basics. So image segmentation is what we do is, given an image, we try to create small patches in the image, and those patches are created based on some properties of the pixels. Okay, so the idea is it could be like some kind of meaningful regions. For example, if you look at this first image, what we can see here is that we can see the clouds. So if we can create a patch which actually cover all these clouds, so that will be one segment of this image. Similarly, you can see that if we try to like isolate all these pixels which are from this lake, then this will be another segment. And again, this for the mountain. And these are all the trees. So this is like a segmentation where you have some kind of meaning to it, some kind of semantic meaning. Okay, so this represents lake, this represents cloud, so on and so forth. And similarly, you can see here that we are again trying to segment these different patches. And in this case, again, you do have some semantic meaning, but you can also observe that most of these parts are like maybe from the same object. All right. So the segmentation, it tries to use some kind of a linear structure as well. So you can have straight lines, something like this, or you can have curves. Okay, so the I think so the interesting question is why we need to do segmentation. And of course, I mean, as a problem itself, it's very interesting. I mean, we would be interested in knowing, okay, what's the fine boundary of the object and what's the exact localization, but there are a lot of applications of this problem. So for example, you can use it for image retrieval, and image retrieval, you have seen that when we're talking about features, so you take images, extract features, and use those features for image search, right? So the same problem, but in this case, you can actually use image segmentation. And then what you will do is you will first perform image segmentation, divide an image into multiple patches, and maybe extract features for those patches, and then perform image retrieval. Then machine vision, this is fine. Like, you want that visual perception, right? So that's a good application. And again, the segmentation is used in medical field a lot, because in medical imaging we do have like CT scans and all those things, where we do need to separate like different parts. So it could be like maybe separating a tumor, or maybe separating some nerves or things like that. So it's very useful in this field. And of course, for object detection, if you want to do like fine grain detection, and so it's a long list, so we don't have to cover all of these, but you get the idea that it's very useful. And it's useful, that's why it's like one of the oldest and widely studied problems. So the initial algorithms were based on region splitting and merging. We will cover these today. And the recent techniques are mainly like based on deep learning, which also try to utilize energy minimization. So we will talk about region splitting merging. We will talk about a very general architecture which can be used for segmentation at a high level. And we won't talk about energy minimization, but I think it's good to know that the optimization is also useful. So if you try to differentiate between what we have learned so far in the course, for example, low level features, so the clear distinction is, when you're trying to extract low level features, you actually don't have a semantic meaning, or you don't have a you I mean you can't say that, okay, this particular area belongs to maybe a certain part of the object, or things like that, right? Because you just find interesting point and you extract features, and those features will be useful later. So this is like maybe at a higher level, where you can say that, okay, if this is a segment in the image, it might belong to a car. So you have that inferencing process, right? And it could be like a more detailed as well. It doesn't have to be at a high level like a car. It could be a segment of a tire itself, but still we know that, okay, this segment belongs to a tire. So we'll have that meaning. So which was not present when you were trying to extract these low level features. Okay, so as I said, there are a lot of category of algorithms which can be used for image segmentation. So the basic one is thresholding. We will talk about this today. Then we have region based. Again, we are going to cover these as well. Then clustering based, we'll talk about these as well. Then we have graph based, shape based, energy minimization. These topics we won't be covering. And then we will talk about how we can use deep learning for image segmentation. So let's try to understand how it works, like when we look at the image itself. So let's try to understand the basics. Okay, so as I said, when you're doing image segmentation, you're trying to partition the pixels into different groups or different segments. For example, if you look at this image, and let's say we have an algorithm which can perform image segmentation, then it might give you something like this. All right. So these are all the segments coming from the input image. And then you can assign, okay, you can say that, okay, this is hand and maybe a face combined. So that's segment number 1. And then this is something, I think, a code hanging over there. That's another segment. And this is like the person itself. All right. So these are all the segments. And it depends upon like what you want to achieve and which algorithm you're using. That it will control like what kind of segments you get. Okay. So when we are creating these segments, the question is how to actually obtain those segments. And usually most of the algorithms, what they do is they perform pixel level analysis and use some kind of similarity criteria. Okay, so this similarity criteria could be as simple as pixel intensity. So now what you do is you let's say if you're considering a pixel at this location, what you will do is you will consider the pixel intensity of the neighborhood. And if you see that the pixel intensity is not changing a lot, it's almost same, you can create a group out of that. Okay. And similarly, you can use maybe the color or the texture, or maybe you can use histograms, or you can try to be more sophisticated. You can in fact use features. The features are matching of small patches. You group them together and you create segments. Okay, so this is very important. Like, what is your similarity criteria? And again, it will vary depending upon the problem. But whatever you do need a similarity criteria. Now let's start with like a very basic algorithm, which is called image binarization. And again, this is also a kind of image segmentation. Now, image binarization, what we do is, I think there is a question from Lawrence. Is the model aware of what the segments are, like object detection, or it's just dividing into regions? Yeah, so Lawrence, that's a good question. So right now, we'll start from the basic algorithms where we won't have any such notion. We will just try to segment it. And later on, we will see we can actually do segmentation and also know exactly what that segment is, the semantic meaning. So that would be like more advanced. But we'll start from the beginning where we don't know, we don't have any information. Okay, so, and again, image binarization, it falls into the first category where we don't know what's the semantic meaning. Now, image binarization, it's actually pretty trivial. What you do is, given an image, all you have to do is, for each pixel in the image, you have to determine whether this is a foreground pixel or it's a background pixel. And again, I mean, it could have different meaning depending upon different images, but foreground is something which is of interest, which you think is like interesting in the image, and background is something which you don't care about, you just ignore it. Okay, so image binarization tries to categorize each pixel in the image into one of these categories. And right here we are showing an example, and you can see that the black color here signifies it's a background. All right, so it's dark, and the lighter pixels, which have very high intensity, are actually the foreground pixels. Okay, so in this case, you can see that on the image on the right, each pixel can only have two values, either 0 or 1. So 0 will be very dark, which indicates background. 1 will be very bright, which means foreground. So it's not even grayscale image. So it's flat 0 or 1. All right, so this process is called image binarization. Let's try to understand how we can actually perform this operation. Okay, so it's actually very trivial, and it utilizes the histogram of your images. Okay, so, and what you do is you have to just pick one threshold, let's say T, and what you do is, depending upon the threshold, you just look at the pixel intensity at each location, and you just do this matching. You see if the pixel intensity is lower than the threshold, you will assign it a 0. If it's greater than threshold or equal to threshold, you will assign it 1. And this simple process will actually divide all your pixels into either background or foreground. Now the question is how to determine this threshold. And I think there is a question from Mert. Eyes of the people are black. Is that a mistake? Or should they be considered background? Yeah, that's a good point, Mert. Ideally, I mean, they are not background, right? They are the salient segments in the image. But in image binarization, we are just trying to make them positive foreground or background depending upon the intensity value. So that's the reason they are turning out to be background. So for this algorithm, it's fine, it's not a mistake. But if you move on to like more advanced algorithms where we not just do foreground background, we actually create multiple segments, then this issue will be resolved. But yeah, that's a good point. Question from Brandon. Would this mean if above threshold then apply the pixel color to be 255 if less than 0. Yeah, you can say that. Yeah, so that's true, Brandon. I mean, you can have you can have 255 and 0. So it's just like you're dividing into two categories. And you can pick 255 for one and 0 for other. And you can also pick maybe just 200 for one and 0 for other. It's up to you. But the question is like you should have two categories, just two. And 255 and 0 is a logical choice because if you visualize that, then you will only see black and white color. Okay. Now the question is how to determine this threshold. So to do that, let's look at the histogram of the images. And what we try to do is, okay, so yeah, this is fine. Okay, so what we do is we try to first visualize the histogram of the input image. And histogram, you already know how to create one. So y-axis is the number of pixels which belong to like each of these intensity categories. And in the x-axis, we have pixel intensities. They will start from 0 and they will go all the way up to 255. So this histogram is actually showing you, let's say if I consider this point and this pixel intensity is maybe 80, and this means, this peak means there are this many pixels which have intensity value 80. Okay, so this is a very traditional histogram. You should all know that. If no, please let me know. I can briefly go over it again. Okay, so then you can, what you can do is, if you plot this histogram, you will get a curve like this, and you can manually visualize the curve. And the logical thing to do will be, because you want to divide the pixels in your image into two different categories, right? And using this histogram, you are clearly seeing like two different peaks, which means that this could be your first category and this could be your second category, right? So all these pixels are actually the brighter objects because it's close to 255. And all these pixels are actually close to 0. So these are the darker objects. And we want to differentiate between these two. So we can pick a threshold at this location, which is kind of a value over here. So this will be, let's say 100. Then the threshold in this case will be 100. And what we will do is all the pixels which have intensity less than 100, they will go to 0. And all the pixels with intensity greater than 100, they will all go to 255. All right. So now the question is, this is a manual process and which is true. And this is a very simple case where we are seeing two different peaks. But ideally, if you have visualized histograms for some of your images, you might have seen that your histogram will never be this simple. It will have multiple peaks. So then you will have to make a decision. So before going deeper into that, how we can actually estimate a threshold in a better way, let's look at some examples. So this is the original image. And if you plot a histogram, it will look something like this. And the reason is most of these pixels are either very dark or they are very bright. Some of these are in between. So it will be pretty easy for you to differentiate between these two. And so this is like one sample example where we pick a threshold based on that histogram. And here you can see that all these are like background pixels and all these are foreground pixels. So this is image binarization. Now let's consider some different variations. In this case, what we are doing is we chose a threshold which was quite low. And in this case, you can see that what happens is most of your pixels are then actually considered as white pixels, which will be like towards high intensity. And you have only few pixels which are considered like darker because you used a very low threshold. And you can see that the details which were the letter over here, they are not seen here. And then you can have very high threshold. So what will happen if you pick a very high threshold, then some of the pixels which were like towards the brighter side, they will also be considered as dark pixels. And that's exactly what's happening here. So all these pixels which were actually kind of close to the brighter side, they are considered as black. and you're not missing actually any of these pixels which were in fact dark. So an interesting observation here you can see is that all these pixels, right, they are dark. So if you look carefully at the image, these are like the shadow pixels. Okay. And if you carefully look at this image, like on the right side, so this is more bright. It means that the light source is actually in the right hand side, and that's why you have a shadow over here. And since this is like closer to the light source, these are brighter pixels as compared to the pixels on the left, and that's why all these pixels are actually clearing the threshold. Okay, so let's look at another example. So this is a fingerprint, and in again we can draw a histogram, and you can see that it's pretty clean. So you can easily select a threshold. So all the left are background, all the right are foreground, and you can see like a very clean binarized image. Now let's look at more complicated examples. In this one, again, it's not that difficult because most of the pixels are dark, and you can see that the darker pixels, you get a peak here, right? Because this is close to 0. So these dark patches belong to this distribution here, and all the background pixels which are brighter, they belong to this peak. And you can see that like there's a valley here. It's not absolute 0. So these are the pixels which have like a value in between. So some kind of noise in the background maybe. Okay, so now what you can do is you can actually look at this histogram and select these thresholds. So let's say we start with the first one. So this value is 110. All right, so then in this case, what will happen is all these pixels will be actually determined as, let's say you are, so in this case you are just inverting this, right? So if it's on the left, you are assigning it a value of 255 because it's white, and if it's on the right, you're assigning it as a value of 0, which is fine. I mean, as I said earlier, I think there was a question that what should be the value. So you can choose whatever value you want, because that will only change like how it will be visualized. That won't change the result. So in this case, you can see that you can easily see these white patches. So this patch is coming from this location. And one interesting observation which you can see is that you also have these small patches in between of these circles. So if you carefully look at these black patches at the center, you can see that maybe if these are like some kind of cells, so then that white patch, a small patch, is the nuclei. Okay, the nuclei of this cell. So, and that's kind of brighter as compared to the cell itself, and that's what we are catching here as these black dots. And these actually belong to maybe the pixels which are shown here in the histogram near this value. Now let's move towards the right. So in this case, let's say we select a threshold of 147, which will be right over here. Then you can see that you don't see those black patches because they might be coming from this region, and these are pretty clean, and even like the background is pretty clean. So this seems like a very optimal solution for this particular image. Okay. Now, if we keep moving towards the right, let's say you pick a threshold which is closer to this leg of this distribution, and this is, let's say, 185. Then in this case, you will see like these scattered boundaries, right? And these scattered boundaries are coming from the pixels over here, because these were actually brighter pixels. And you can see that it's kind of a merger between, it's the boundary of those cells. So it's a merger between the background and the foreground. So there will be like some distortion there. So these pixel locations are exactly reflecting that. Again, which says that this is not a good threshold value. So it should be lying somewhere at the center. Okay, so any question on this? We have a pop quiz based on this. So if there are any questions, please let me know. Okay, all right. Now, again, so let's consider the same image again. We are interested in this particular patch, All right. And for this patch, this is the histogram. There's the same, exactly same which we saw in the previous slide. All right. Now the question is, if we are going to use a threshold of 45, then which of these two statements will be true? The first statement is the black patches will not be visible. So these are the black patches. So this is saying that if you use the threshold of this, then you will not see any of these black patches. All right. The second point is saying the black patches will be clearly visible, but some pixels from white regions might be also detected as a patch. So this statement says that these black patches will be clearly visible. It means you will have these nice boundaries, but some of the pixels in the background, they will also be considered as foreground. So there is a question from Sadia. Can you repeat the criterion? So which criterion you are talking about, Sadia? For idle threshold. Yeah, I didn't quite get your question. Threshold means, so we discussed these threshold values, right? And if you select each of these thresholds, you will get different results. So I don't understand what do you mean by criteria. We don't have any criteria here. Probably we can cover the question after. So I think it's sufficient time. Okay. So okay, so let's discuss like what will happen if you use a threshold of 45. So this 45 will be roughly here, closer to the darker values. All right. So if you use a threshold of this, then all the pixels on the right, they belong to one category, right? So most of these pixels will be either white or black, depending upon like what you choose. So let's say you consider white. So all of these will be white, which means that you won't be seeing any black patches. They will be completely gone. So the only thing which will be visible is the pixels which are on the left, and these pixels are the darker pixels. So it could be that some of the darker pixels which are maybe in the boundary of these cells, they might be visible, but again, it will be just scattered pixels. So it won't be like a complete black patch. Okay. So I think most of you got this right. Some of you have said B. I'm not sure why. And okay, so now we can go to your question, Sadia. So you're talking about some idle threshold. Do you want to rephrase that? Or, or it's clear now? Okay, you were discussing middle region is better. Right, so middle region is better because we see this result, right? Where you have very nice boundaries, and again, so that criteria will depend upon what kind of results you want. So for example, if you're not interested in the nuclei of the cells, then this could be a good result. But if we are also interested in the nuclei, then this might be a better result. So it all depends. Okay. So that's good. Now let's move on. So let's talk about Otsu algorithm. So right now the limitation of image binarization was how we can determine which threshold to choose, because it was a manual process. And I mean, basically we don't want to do that, right? For every image, there should be some algorithm which should do the task and tell us, okay, this is the threshold and that's your result. So that will be an automatic process. You don't need any manual involvement. So that's exactly what this Otsu algorithm is going to do. Okay, so what it does is it takes a grayscale image as input. It first computes the same histogram which we discussed, and it tries to find a threshold which actually meets the criteria. So now we are talking about criteria, Sabia. Okay, so now that criteria is we have to maximize the between class variance. And if you have done like your statistics class, well, you should know what a class variance is, but I can explain that to you like at a higher level. So variance is something, if you have a set of points, how distinct their values are. Okay, so for example, let's talk about maybe the current class, which is computer vision, and let's say all of you received a grade A, let's say in your midterms. So then what will happen is we have these data points, which is like number of students, which is 94, and all the 94 values are all A, which means there is no variance, right? No variation at all. So then variance will be low. But if there is a range, like some students are getting maybe F, they are failing, some students are getting A plus, some are getting B. So there is a variation in the distribution, right? And then that means the variance will be high. So that's the idea of variance. So just consider the same concept here. So this is between class variance, which means that you have two classes. One class is foreground, one class is background. And what you want is, if you consider data points in those two classes and compute the variance, it should be very high. So you try to maximize it. And then what will happen is, if you try to maximize it, it will ensure that the samples which are in category 1 are actually quite distinct from the samples which are in category 2. All right. So that's the high level idea. And there is a simple formula how you can compute between class variance. We don't have to go deeper into that. So for a programming assignment, you can just use this formula. So the between class variance, if you have the probability for those two classes as P1 and P2, and you have the mean for one class, which is mu1, and mu for like all the data points, which is like the symbol mu, then you can simply use this equation, and you can also simplify this to maybe just P1 times P2, mu1 minus P2 whole square. So what this means is you have the probability for the first class, probability of the second class. You compute the distance between the mean of those two classes and just take the square and multiply. Okay, so that will give you the between class variance. Now the question is, how do we get like these probabilities for those two classes, and how do we get these means? And again, we'll go through this. It's pretty simple, but before that, first try to understand a relation between P1 and P2, because we only have two classes. One is background, one is foreground, which means that if the probability of a pixel belonging to foreground is P1, then the probability of a pixel belonging to background will be just 1 minus P1, because the sum of the probabilities should be 1, which means that if you have probability for 1, you can easily compute the probability for the second one. And that's we are going to use to update the formula. Now this is don't this is a pretty simple algorithm. You don't have to be worrying about this by seeing all this maths. I will explain this algorithm like by going over this histogram here. And this algorithm is, what it's trying to do is, it's trying to just find out the optimal point, the threshold point, which will maximize the interclass variance. All right, so that's exactly what this algorithm is doing. Now, before going through the algorithm, let's first try to understand how you can compute P1 and P2 and mu1 and mu2, because that's exactly what you need to compute between class variance. Okay, so again, this is pretty simple. So P1 is the probability of a pixel belonging to, let's say, foreground class. So P1 is, let's say, foreground. So if you have to compute the probability, that simply means if you select a threshold at this location, all the pixels on the right, they are foreground, right? And all the pixels on the left, they are background. So the probability of a pixel of belonging to a foreground will be, you can just sum all these pixels. So all these pixels divided by the total pixels in your image. So that's the probability, right? And to get the probability of a pixel so that it belongs to the background class, you just take all the pixels on the background. You just sum all these pixels and divide that with the total number of pixels. So for example, let's say you have 100 pixels in your image, okay? And you set some threshold, and using this threshold, you have 20 pixels in foreground and 80 pixels in the background. It means that your probability P1 will be 20 over 100. Okay, so that's 20%, or you can say 0.2. And the probability for the background will be 80 over 100, that will be 0.8. So it's pretty simple. You just see like what's the proportion of pixels in those two categories. So I'm explaining it pretty well. If there are any questions, please let me know, because you do have to implement this for your programming assignment. All right. So that's simple. You just compute P1, P2. And this is like how you compute the mean. So mean is, again, you can just use this formula. So I is, I think there's a question. How do you decide the threshold? So that's exactly what we're going to find out. Okay, so that's exactly what this algorithm will give you. We don't decide any threshold. Yeah, probably I think I get what your confusion is. Just hold on for maybe, yeah, use the threshold. Just hold on. I think as we move forward, your doubt will be clarified. So now let's, so before going to that, let's talk about how you can get the mean. So mean is again, just computing the average intensity of these pixels. All right, so it means that, so average intensity, the simple way to do that will be, you can take intensity of each pixel and sum it over the entire image and divide by the number of pixels, right? So that will be your mean intensity. So you're doing exactly the same thing, but you are doing it partially for these pixels, which are either background or either foreground. So this is just averaging the intensity of the pixels which belong to a certain category. Okay, so that will be your mean. Now let's go to like the question from James, and I think that's a very good question. So again, I'm not going through this algorithm. I will first explain the process, and then we will go through this so that it's pretty easy for you. Now what you do is, once you know how to compute P1 and P2 and mu1 and mu2, and we have this formula P1 P2 and the subtraction square. So this formula you can update as P1 and then 1 minus P1, right? Because sum should be 1 and you're taking the difference and squaring. So now what you do is, once you know all this, you start from the left. Okay, so left is like 0, the starting point, and you set your threshold to 0. Okay, so that was the question. How do you set how do you decide your threshold? Okay, so James, that's the answer to your question. You set your threshold to 0, then you compute P1, compute P2, compute mu1, compute mu2, and then apply this formula that will give you the interclass variance. All right, which means that when your threshold is 0, you have a corresponding value for interclass variance. Now what you do is, you repeat the same process for all the intensities. So you start from 0, you go to 1, go to 2, 3, 4, keep going. And for all the pixel intensities from 0 to 255, you will have a corresponding value which will represent the interclass variance. Now it's pretty simple. You just take the maximum of that because you want to maximize your interclass variance. Then what that will do is, for one of the pixel intensity, you will have a value of interclass variance, which will be maximum among all the values you have. And that will be your threshold. So does that answer the question, James? Okay, great. So now, and this algorithm is exactly doing the same thing. So you set u is equals to 0, which means you are starting from the left, and you will go all the way up to G max, which could be like 255, the maximum intensity you have. Okay, so you compute the histogram for the image. So this is the histogram. And then what you do is, you compute the probabilities P1 and P2, for these two classes depending upon the value of u. All right, and then you just compute that interclass variance for that particular value of u. You know the formula, and you keep a value. You keep storing it, which is like the maximum interclass variance. And what you do is, if the current interclass variance is greater than what you have stored earlier, then that's your new interclass variance, right? So this is just bookkeeping. So this is just trying to find out which one of them is maximum. And then you do the increment. So keep moving towards the right. And at the end, what will happen is you will find out, okay, which was the maximum interclass variance, and you just pick that threshold. Okay, so that's the algorithm. Question from Sayed: the while loops find the S max. The while loop will, yeah, it will find the S max, but we are not interested in S max, right? We're interested in the intensity at which you get S max. But yeah, S max will also be an outcome. Is it clear, Sayed? Because for threshold, we will need the intensity, right? Okay, good. So I think there's another question. So please ask any questions you have. As I said, this is going to be a programming assignment 3 part of it. So you will have to implement this. And again, don't use existing libraries to which actually do also. You'll have to write your own code to implement this algorithm. Okay. And I mean, you can use maybe some of the, you can use maybe how to compute a mean. You can use mean library for that. That's perfectly fine, because that's a very trivial thing. And I think there is nothing else where you can use library, but this algorithm you will have to implement. Okay, so question from Ahmad: can you explain step 9 again? So step 9 is, so okay, so you start from u equals to 0, right? Which means you start from the left, and you, okay, just give me a second. All right, okay, so you start from the left, and this step is just saying that you keep incrementing towards the right. So you first start with 0, and then this will be t0 equals to 1. So it will be 1, then it will be 2, 3, 4, all the way up to 255. Here it's just used as a increment variable t0, and you can set it to 1, you can set it to 2. So okay, so that's clear. Question from Brandon: couldn't you loop through the bins, aka the groups of color values? Yeah, Brandon, I didn't get your question. Why you want to loop through the bins? Yeah, I mean, I think in a way you're doing the same thing, right? So these bins are, so for each pixel intensity you have a bin. So essentially you're doing that. So you're going to each bin and saying that, okay, if this is a threshold, then what is the interclass variance? Then you check for the next bin and keep doing that. So you essentially test for all the bins, and you select the bin for which you get the maximum value. So I hope that's clear, Brendan. If not, I think please try to rephrase it. Okay, question from Amelia: why do we start at 0 instead of 1? I mean, it's fine, you can start from 1. That's fine, because 0 is like the least intensity, right? And of course, I mean, that will never be the case. So you can optimize your algorithm and save one step and start from 1. That's perfectly fine. Okay, question from T0. Okay, I think we covered that. That's clear. That's clear. All right. Okay, so there are no other questions. If I missed your question, please let me know. So that's O2 algorithm, and let's try to see some results. So this was your input image, and we use the O2 algorithm to find the threshold, and you can see like it's doing a pretty good job. And this is like, you don't have to do any manual selection for the threshold. It will try to automatically find it and do the image binarization for you. Okay. Now, okay, so yeah, this is a very nice visualization. If you didn't quite get like how it works, so as I said, you start from the left and you keep moving towards the right. And again, you don't have to do that. You can start from whatever point you want. It's just like easy to write as algorithm. but essentially you need to find the value for all the pixel intensity locations. That's it. Okay, and going from left to right is easy, and of course you can go from right to left as well. You can start from 255 and go all the way up to 0. So the order doesn't matter at all. So let's say we start from left. So this line is actually indicating for which pixel intensity we are computing the interclass variance. The blue one is the histogram. So this is the histogram using the pixel intensities for the image which I showed you earlier, this one. And the red color is actually showing you the interclass variance, which you compute for each pixel intensity. Now you start from 0, and as I think there was a question from Amelia, why do we start from 0? So you can see that when it's 0, almost 0, right? So there is no variance at all. And the reason is when you start from 0, then all the pixels are essentially like belonging to one class. So we didn't find any variance, and that's why the variance is 0. Now, as you keep moving towards the right, you can see that the variance is increasing, and it keeps increasing. And at this particular point, you can see that it's kind of capping over here, right? So that's the maximum interclass variance you can find. And after that, if you move towards the right, it started to drop. And then that's all you have to do. You have to find this point where it's maximizing. And corresponding to that pixel intensity, that will be your threshold. All right. Okay, so that was image binarization. Now let's move on to region-based segmentation. Question from Fernando. In practice, is Otsu thresholding faster than canny edge detection? If we are okay with having an approximation of the edges. That is an interesting question. And I think the answer to that is, first of all, both are solving different problems. Otsu algorithm is not going to give you edges. Okay, it's just saying foreground or background. And unless you have just edges in your image, even in that case, yeah, in that case, I think you will get all the edges and you can use it to get the edges, but practically when it won't happen, right? You will have other structures as well. But canny edge detection is like essentially giving you the edges. So each pixel, it's saying it's an edge, it's not an edge. But Otsu is just saying it's a foreground, it's a background. And it may happen that if you, let's say, have a solid region, then all the pixels in that region will be foreground. So I mean, you can't say like which of the pixel is edge, right? So I agree, like for some of the cases, in very special cases, you can use Otsu for edge detection, but I won't recommend that because that's not what like this algorithm is solving. And so that's the first part. The second part, I think Otsu will be faster because we saw the algorithm, right? It's just iterating and computing that number. On the other hand, in canny edge detection, it's a long process. You do filtering, edge detection, then a lot of post-processing, which is computationally complex and will definitely take more time. Okay. So now let's move on to, so that answered the question, Fernando? Okay, great. So let's move on to region-based approaches. We have two. And so the idea is, let's say this is your full image, and this is kind of the high level segmentation where you're saying that all these pixels belong to a particular object. And this is like the other extreme where we just have a pixel where we say that, okay, this pixel belongs to, or you don't say belong to, you just say that, okay, what's the intensity? You don't have any other knowledge. Okay, so these two are the extremes. Then segmentation is somewhere in between where you will have grouping of these pixels in form of segments. All right. So these will be like, these will give you some kind of closed boundaries. You can call these segments, you can call these regions. And as explained earlier, you use some kind of similarity measure to actually figure out whether two different pixels belong to the same region or not. So in region-based, what we do is we actually used two kind of measures. The first is the intensity. It could be just a grayscale intensity, or it could be the color. And the second is the spatial proximity, whether those two pixels are close to each other or not. Because what may happen is you might have a pixel, let's say at this location, which could have exactly the same intensity as a pixel from like the other part of the image. But again, we can't say that, okay, these two are the same segment, right? Because of their proximity, they are far away from each other. So we use these two criteria to create these segments. Okay, so let's go through how merging works. So in merging, what we do is we randomly start from any pixel, and then we search like in the neighborhood, and we try to find some similarity measure between the current pixel and the neighboring pixels. And if we find that they are similar, we create a group, and we keep doing that until we are finding similar pixels. So that's how the this approach works. So this is also called region growing. All right. So the algorithm, again, it's pretty simple. What you have to do is you can actually compute the absolute intensity difference between two pixels, and you will have to use some kind of threshold which will say that, okay, they are similar or not. And then what you do is you keep computing a running average of intensities. Okay, so what will happen is if you don't compute average, then it may happen that, let's say for example, if you have an image, let's say where you have 100 pixels, and each pixel is one number starting from 0 to 100. So it could be like 0, 1, 2, 3, 4 continuous numbers. And let's say, like, luckily I started with a number 0, and my threshold is 2. Okay, so if the difference is less than 2, I will say these are neighbors or these are the same segments. Then what may happen is I can start with 0, I will go to 1, I will say, okay, 0 and 1, they are close together because the threshold is less than 2. I will say it's the same segment. Then I will start from 2, go to 3, again same segment, and I can go all the way up to 100, and it will be just one big segment. But then you look at like the values of the pixel from which you started, which was 0, and the pixel which you ended, which was 100. The difference is 100, but your threshold was just 2. And so that's why it's very important you keep computing the average. All right, so that's called running average. Then that's the second important part. Then the third important part is you try to monitor the standard deviation in the intensity. Okay, so it's not just a difference, the absolute difference between the intensities. You also try to monitor like how much is the deviation, how much is the variance. If the variation is high, you won't add like new pixels. But if the variance of the standard deviation is low, you will keep adding. All right, so these are just two, three different terms which will be used. And again, you can use like any combination of these two. So let's go through like a very simple example. Let's say we have a image patch from a big image, and these are the pixel intensity values. So the underscore is showing like the initial seed pixels, which we are taking as a starting point. Now, in this case, the pixel intensity is 1. In this case, it's 7. So let's consider this one first. Now, next, what we do is we consider all the neighbor of this pixel. And we'll have to set a threshold. And let's say we set a threshold of, in this case, 2. So if the difference is less than 2, we keep adding. So let's look at this pixel. So 0, it's clearing the threshold. 1 is clearing the threshold. This is not clearing the threshold, right? So this will not belong to this. But 0 is clearing. Then what you keep doing that, and this is again, you will have to do depth first search or any maybe breadth first search, those algorithms. Then you keep looking into the neighborhood. Then 1 will be again clearing the threshold, and all these will create the threshold, right? So this will be like your one region, which is indicated as A. All right, and starting from this seed pixel, all these will be termed as B. Okay, because all of them are clearing the threshold. So this is good. And as I said, image segmentation, it has a like very wide range of application in medical imaging. So these two are like segmentation in CT scans. And in this case, what you want to do is you want to like separate like these regions. So in this case, again, the region merging was used, and you can see that you get a very nice segmentation for this image. And again, in this one, if you start this as a seeding point, this red cross, you will get a segmentation like this. Okay, so I think there is a question from Amelia. Do we look at just the adjacent pixels, that is above, below, left, right, and not diagonal? Does that depend on the algorithm? That's a very good question, Amelia. So that will depend on the algorithm. And I think this we have discussed. Yeah, we have discussed when we we're talking about connected components, right? So this is called like connectivity. So you can have 4 connectivity, you can have 6 connectivity or 8 connectivity. And ideally in this case, most of the time it will not matter, because if you're just using 4 connectivity, then in the next iteration 4 connectivity of that pixel will be like similar to, I mean, it will include some pixels which will be 8 connectivity for the first pixel, right? So eventually you will get all. So it's I think it's more of a implementation detail, but it's not going to change the result. So I hope that's clear. Now let's try to understand how this algorithm works. So you start from a random seed. Okay, in this case, let's say this, and let's say just change the number of -1, which indicates that, okay, you are at this particular pixel value, and you have to consider this and have to compute, go through the neighboring pixels of this location. And you keep maintaining a queue, or it could be a stack. And again, it depends like which algorithm you're using. And I'm sure all of you must be familiar with either depth first search or breadth first search. So depending upon which algorithm you want to use, either you maintain a queue or you can maintain a stack. But again, it won't change the final results. It's just like the order in which you are processing the pixels that is going to change. Okay, so that's the starting pixel. The next step is you look at like the neighborhood. So let's say we are talking about 4 connectivity here. Okay, then you mark this as done, and then you add like these neighboring pixels to the queue or to the stack depending upon the implementation. And then you take like one of the element from that stack, and then you start processing that. So let's say we pick this one, then we process this one, so then we have to add this and this one. So this pixel will not be will be added because it's not clearing the threshold. All right, so you keep doing that, and at then what will happen is you will get your region something like this when you're done with all the pixel locations. Okay, so that was region growing. So let's try to compare this with normal thresholding. Let's say we have a patch like this, and for thresholding we can actually use Otsu, or you can do it manually. Let's say we have a threshold of 10, which says that if the pixel intensity is greater than 10, it will be foreground, otherwise it will be background. So you will get something like this, and you can keep varying the threshold. So for threshold 12, you will get something like this. All right, so these are the results from thresholding, and the result depends upon like what threshold value you are using. Now, if you look at region growing, so again, in this case, you need some parameters, and the parameters are like what should be the value of the variance, and again, like what's the value of the threshold which you're considering. So in this case, let's say we're considering a threshold of 11. So this should be the segmentation, but what your region growing will give you is something like this. So all the purple locations will also be added to the foreground region, and the reason is this the setting of this variance. All right, so you start with this location, then 9 will be considered as a grouping because it's clearing the variance threshold, and similarly you will keep going, and then you will find that all these pixels are also getting added to that region. So that's the difference between how thresholding works, how region growing works. So of course, like you have a lot of computational overhead on this algorithm. Thresholding is pretty simple. So that was merging, but again, we can actually do a different go a different direction, which is called a region splitting. And in this case, what we do is we start from the top, and then we split to the bottom. All right. So it's different. It's different from the region merging we discussed. I think there's a question from Curtis. The variance allows for under the threshold. Right. So variance is like is like a, you can say a limit you want to put, like whether you want to consider the pixels as neighboring or not. Okay. So threshold was just like the starting point where you say that, okay, this is the foreground, this is the background. So that was just one value, but variance is actually more of a looking at the proximity as well, right? If a pixel which is, let's say, not clearing the threshold, but it has like a value which is close enough to that threshold, and it's actually also close to that pixel which is clearing the threshold, so then you will count that in. All right. So I think there's another question from Rochia. Can you repeat the variance part in the last slide? Okay, so variance, right now it's not exactly variance. So this is like a threshold which you consider when you decide whether two neighboring pixels belong to the same segment or not. So in this case, what you will do is if you subtract these two values, so that will give you 5, but your threshold is 2, which means that these two doesn't belong to the same segment. Similarly, you can do that for 11 and 12. And similarly, you can do that for 11 and 9. Right? So if you subtract 11 and 9, that will give you 2. So that's clearing the threshold. And that's why you count this in. Okay. Okay, question from Carlos. Adjusting the threshold will eliminate the variance. Adjusting the threshold. Not entirely, because in this particular case, it might be true. But again, you might have a different distribution, right? Okay, so region merging, it's again a very pretty simple algorithm. You start with a big region. So in this case, let's consider just the binary case. And you can easily extend this to like maybe grayscale or even something else. It's all about like how you compute the similarity, right? So in this case, it's binary. So we know that if the pixel intensity is same, these are neighbors. If not, they are not. So we are just keeping it simple. So this is the image patch. All these are darker pixels, all these are brighter pixels. So what we do is we take the initial patch, we divide into 4 regions, all right? And then what we do is for each region, we figure out if all the pixels have same intensity or not. So in this case, they have. So we stop there, we don't do anything. So this is the starting point. So you can say that this is level 1, which is like the full image. And you have to first consider whether all the pixels in this image are same or not. So they are not same here, right? Some are white, some are black. So then what you do is you divide this image into 4 different regions: 1, 2, 3, and 4. All right. So 1 is like this one, top left. 2 is this one. 3 is this one. Okay. 3 is this one, and 4 is this one. And you can give any number, that doesn't matter. And this is called region adjacency graph. Now let's consider the first region over here on the left, right? So all the pixels are of same intensity. So we don't break it further. And that's why the graph is ending here. It's a leaf node, right? Now let's consider second. So this is the second one. And in this case, you can see that, okay, some pixels are white, some are black. So we'll have to break it down. Okay, so we break it down into 4. Again, we will get similar regions 1, 2, 3, and 4. So these are the 4 regions. All right. And again, let's go to the third region here. So this is the third one. Again, we can see that all the pixels don't have same intensity. So we'll have to break it again into 4. And that's exactly what we are doing here. And so we keep doing that until all the pixels in the region are of same intensity. And essentially, if you just reach to single pixel, it will happen. Okay, for example, in this case, you'll have to go like to the individual pixel to actually stop. And you're stopping over here. All right, so this is called RAG adjacency graph. And this is your level 1, which is the full image. Level 2, like when you divide into 4 regions, and you keep dividing and you keep increasing the level. So in this case, this RAG graph has 4 levels: 1, 2, 3, and 4. Okay, so we start from the top. So the whole image is called level 1. Okay, so question from Sadiq, can you explain one more time? All right, sure. Okay, so this, you understand, this is your image. All right. Now what you do is you create a node in your graph or in your tree for that image. So this is your node. All right. Now the next step is you go through each pixel in this image and you see that whether all the pixels in this image have same intensity or not. Okay, so that's a binary decision you have to make. If all the pixels have same intensity, you do nothing, you are done. If they have different intensity, you divide that image into 4 regions. So a straight line like this and a straight line like this. So these are like 4 equal sized regions, and for each region you will create a leaf. So this is 1, 2, 3, 4. So these 4 leaves correspond to these subregions here. All right, and then you just repeat that process for each subregion. Okay, question from Sadia, different by how much? So that's what I said, right? So you should have a similarity measure which should tell you, okay, whether the pixels are similar or not. And in this case, we are just considering binary case. So the pixel is either black or is it white? So if all are white, it means there is no difference. If all are black, no difference. But if some are white, some are black, it means there is a difference. So we'll have to break it down. But again, you can easily generalize this to maybe a grayscale image where you can have a threshold which will tell you whether 2 pixels are similar or not. So that's exactly like what we did earlier, right? When we were region growing, then we have a similarity measure, some threshold, which will tell you whether these 2 pixels belong to the same region or not. So is it clear, Sadia, now? Okay, great. So you keep repeating that until you get a region where you don't have any pixels with a different set of intensities, right? So then I was explaining, so this is your level 1, level 2, 3, 4. So this tree has 4 different levels, and this is called quadtree. And what you have is you also keep a piece of information which tells you if 2 different regions are neighboring or not. Because essentially what will happen is you will have to actually use this graph to create foreground and background, right? And you need to know if 2 pixels are neighboring, because if they're neighboring, you will have to join them together. So you just keep a bookkeeping for that, and that's pretty trivial because when you're dividing, you know that these 2 regions are adjacent, these 2 regions are adjacent. Okay, so then you can just connect all those. So in this case, that's the connection. And these regions, if you go through this, 4 is this one, right? 4 cross 4 is just telling me the resolution, and this one is again this region. Again, these 2 are connected, that's why you have a red connection. And again, these 2 are connected, right? And then this 1 pixel is this one, so this is also connected. So this is like one region, and this black over here, it is not connected to any of these. This is over here, so this is a different segment. All right, now, and this is again the same algorithm which I discussed. You keep dividing. So you can say that, okay, you have a function which will tell you whether all the pixels are same or not. So you can call that inhomogeneous, and it could be anything depending on the problem. And you just keep dividing until all your pixels in the region are similar. Okay, so let's quickly go through this example. This is your image patch, and I mean, we can clearly see that the pixel intensities are different. So we'll have to break it into 4, and that's exactly what we're doing. Okay, so we go to second level. So this was level 1, we go to level 2. So don't confuse with the split one. So this is level 2. And now what we'll do, we'll have to go over all these subregions. Again, we see this, we see, okay, it's not all the same. So again, we'll have to break it up, right? So we break it into 2, and we look at this, we say that, okay, these are all same, so we don't have to break this. All right, so in this case, you can see that we stopped here. Then this one, again, we'll have to break it down. We are breaking, and this will have to break it down. So we are breaking into 4. And again, you keep doing that, and you can see that at the end, what will happen is you get all these subregions where the pixel intensities are homogeneous. All right, and then you can connect like all these to get the segments. So now let's say you have this example. The question is how many levels you will have in the DAG graph. And to be clear, as I said, like this whole image is level 1, and if you have to break it down, that will be your level 2. So the question is, after the algorithm, You will have the DAG graph, how many levels that DAG graph will have. Yes, this is a pop quiz. It's, yeah, Amelia, it's levels. How many level you have? Sorry if my speech was not clear. Some of you are saying two. So I wonder why. I mean, you didn't follow the algorithm? Because two means like, so this is level 1 and 2 will be like, you just divide this into 4. But I can clearly see that, mean, even if you just like look at this block, I mean, this is not homogeneous, right? You have 2 and 3. Okay, so the answer is 4. And a quick way to find that out is you look at the region which is like most inhomogeneous, right? And in this case, this is the one, because this is clear. I mean, all are 1. We don't have to worry about this. This is clear. All are 2. We don't have to worry about this. So this is the culprit here. So we'll have to divide this into 4, and then again this 3. We'll have to divide this one, right? So we'll have to go all the way until like 1 pixel. So again, this will have 4 levels. So first image, second this smaller one, third these 4 pixels, and fourth just 1 pixel. Okay, so that's all I have, and next time we're going to talk about slick algorithm again for image segmentation. That is very interesting application of clustering. So if you have learned that algorithm in machine learning, I think it will be very interesting for you to see like how it can be applied for computer vision. Okay, so if there are any questions, please let me know. Otherwise, we can end it here. Yeah, I think we are almost out of time. So let's end it here. Any questions, just write me an email. All right, and I will see you next week. Thank you. Bye.